All right, all right, all right. Just make sure everything is looking good. All right, so let's finish with an idea that we started with yesterday. Hey, what's up, man?
Well,
There, man. How's everything?
they gave me two meals. I told them I didn't need two, but still give them.
No, take it, take it. Here you go. How are you? So I gave you back exam two, right? I see you're good, you're good, you're good. All right. Yep. Yeah. Mm. You did? I'm so sorry. Oh, I'm so sorry about that. Oh my gosh. I'm so sorry. My grandfather was like that. He was the last one. Yeah. Yeah. Right? True, true. Yeah. Yeah. He is blessed for sure. Um, this is take home, so just give it to me tomorrow when you're done. Yeah. Yeah. So, but I have a lesson for today though.
Focused on, I didn't go to it, I was focused on like the homework
Mhm.
because I'm getting it.
Good. Good, good, good.
Going through it,
Yeah.
you know, I tell my argument, I'm like, babe, you know, this is poetry's basic pattern of drafting.
It's true.
That's
Yeah.
what it is, straight
It's
up,
true.
yo.
Yeah. It's true. The for the homework is everything not due till like the 27th, so take your time. Now I ain't finish everything. I'm gonna finish everything today. And I do owe you guys some videos. So yeah, like you might not understand all of the homework, and that's okay. Yeah. It's fine. It's fine. When rest of the class gets here, I'm gonna show you guys the study hall schedule. It's gonna be you guys have options, which ones you guys want to go to. I'm gonna run one of them. You can go to mine or you can go to anybody else's. No pressure. Yeah. All right, so real quick, just want to finish up an idea from that we had for yesterday. So we have several formulas for confidence intervals for the population mean mu. How do we choose an appropriate one? We need to look at the sample size, the distribution of the original population, and whether or not the population standard deviation sigma is known. All right? One second. It's all good. Here you go. Here. So it's take home. Just give it back to me tomorrow, all right? Yeah. In the meantime, though, do you want to do one or two? Want to do test one?
I'll take lunch to see how that. Yeah.
I mean, I let you do corrections, right? So it's all good.
I'll do that. I think you should go.
The tutoring, and then hey, you just take it. Good, good, good. You just take it to tutoring, and then you get back half the points that you miss.
Yeah, Professor, my Spanish is already.
Okay.
I told her I would show you. I don't know if she's sick or something.
Yeah, it's fine. Yeah, she got the test already, so it's fine.
No, for this one, I think she needs.
Oh, she didn't get it
She
yet?
wasn't here, she not, I don't know if she
Yeah.
come in, but
Alright.
you said this is due tomorrow in class.
Yeah, yeah,
So
yeah.
that's why, maybe I could tell her, she gotta come today to get it, right?
Yeah, yeah.
Yeah, I'm gonna tell her,
Yeah.
Professor.
Even if she don't want to stay, she just want to like
Yeah, come and get it.
Yeah,
Because,
yeah. All right.
Well, you're not really seeing it right now, but you did good. I like it.
I did them smaller so they.
Yes.
So that was like that.
They look like yours, natural. That's why I like it.
You finding earthy today?
Yeah, yeah.
I'm just trying to get over it.
Yeah.
Like the mama. Hey, what's up?
Yeah.
Do you have to piece of paper?
Yeah.
Like, it has writing and not blank. If you want though, you know that computer lab that we walked past? Yeah, they have printer paper in there. The printer don't work in there, so actually I'm lying. The computer for the printer don't work in there, so the paper is just sitting there. So use as much as y'all want, you know? Yeah. Hey, did you get test three? Did I give you back test two? I did? All right, that's fine. Okay. So it's take home. Just give it back to me tomorrow. Yeah. 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 Like, what, test three?
No,
No.
the one before.
Yeah, yeah, yeah. Unless you want to do test corrections, and you go to, so you're good. You're good to go. Yeah, yeah. Oh, I clicked the wrong thing. I'm over here looking at this like, yo, what is this? Okay, I'm sorry. I clicked the wrong thing. All right, anyway, let's continue, right? You took one piece. You ain't see that stack? You ain't see the stack of paper? Uh, so let me tell y'all what happened, right? So it happened this semester too, right? So they upgraded from Windows 10 to Windows 11. Microsoft decided that they're going to discontinue Windows 10 for whatever reason, right? Long story short, in the computer labs, right, they have these super old computers that are connected to printers, right? So you have to log into that, you have to turn on that computer and then swipe your card in order to print, right? Problem is the computer can't turn on. So the paper just sitting there. So now you can't print at all. If you want to print, you gotta go to the library. But I'm saying all that nice, clean paper is just sitting there, you know? So you might as well, if you want to grab a stack. That's what I'm saying. Yeah. All right. So let's just summarize real quick what we did yesterday, and then we're gonna move on, right?
Yeah.
So confidence intervals for the mean, right? Assume that you have a random sample of size n from an X distribution and that you have computed the sample mean X bar and a sample standard deviation S. A confidence interval for mu is X bar minus the margin of error less than the population mean, less than the sample mean X bar plus the margin of error, where E is the margin of error. So how do you find E? It depends on how much you know about the X distribution, right? So here's situation one. Situation one is what's on your final. Hint, hint. All right. So you don't know the population standard deviation sigma. In this situation, you use a t distribution with the margin of error, right? So the margin of error E formula is equal to t critical times the sample standard deviation over the square root of n, where there's a degrees of freedom of df is equal to n minus 1. Although a t distribution can be used in many situations, you need to observe some guidelines. If n is less than 30, x should have a distribution that is mound-shaped and approximately symmetrical. It's even better if the x distribution is normal. So if n is 30 or more, by the central limit theorem, it implies that these restrictions can be relaxed. All right. Situation. This is in chapter 8 on the formula sheet. Right? So yeah. I'm just summing it up real quick. No. Yeah. So for situation 2, which almost never happens, and it's not happening on your final, this is just for your homework, right? You actually know the population value of sigma, right? So you know the population standard deviation. In addition, you know that X has a normal distribution. If you do not know the X distribution is normal, then let me finish your thought. Let me finish your thought. 1 second. It's gonna be good. It's gonna be good. I'm coming now. I'm coming. All right. Okay. All right. Then your sample size n must be 30 or larger. In this situation, you use the standard normal z distribution with the margin error. So you have margin error formula is equal to z critical times the population standard deviation divided by the square root of n. This is for homework. All right. Now, which distribution should you use for the X bar distribution? Examine the problem statement, right? If you know sigma for homework, right? You use the margin error E is equal to Z critical times the population standard deviation over the square root of N. If you don't know sigma slash your homework slash your final, right? You use a student's T distribution with a margin error where E is equal to T critical times the sample standard deviation over the square root of N with the degrees of freedom of N minus 1. That's it in a nutshell.
This week, right?
Mm-hmm.
Yeah.
All right. Yeah, for sure. No. It's 2 steps, like 2 or 3 steps.
No.
Yeah.
It'd be like 5 steps.
Now the one,
For 5 steps.
no, that one is coming today. The 5-step one. That's today. Yeah, that's the problem that we're doing today. The 2-hour one. I just want to make a real quick comment about this. All right. So to find confidence intervals for mu based on small samples, we need to know that the population standard deviation is approximately normal. What if this is not the case? The procedure called bootstrap utilizes computer power to generate an approximation for the X bar sample mean distribution, right? Essentially, the bootstrap method treats the sample as if it were a population. Then using repetition, it takes many samples, often thousands, from the original sample. This process is called resampling. The sample mean X bar is computed for each resample and a distribution of sample means is created. For example, a 95% confidence interval reflects the range for the middle 95% of the bootstrap X bar distribution, right? So if you read using if you read using technology at the end of the chapter, you will find one of the bootstrap methods, blah, blah, blah. Okay. That's for grad school. That's not for us today. All right. Remember, I want all y'all to be doctors when y'all grow up. All right. Yeah. All right. We all trying to make 7 figures when we grow up, right? All right. Per month or per year? Which one we doing? Per day. That's what I'm talking about. That's what I'm talking about. Most definitely. All right, so this is what we're getting into today. All right. This problem has a whopping 5 to 7 steps. Right? I promise you it's mad easy though. I got you. We're gonna get there. We're gonna get there. So look, we're getting to an introduction to statistical test. Right? Knock out the test, man. Knock out the test. Knock out the test. Here. This is being recorded, so you can watch it back. Here. All right, so in chapter 1, right, we emphasize the fact that one of a statistician's most important jobs is to draw inferences about populations based on samples taken from the population. Most statistical inference centers around the parameters of a population, often the mean or probability of success in a binomial trial. Methods for drawing inferences about parameters are of 2 types. Either we make decisions concerning the value of the parameter, or we actually estimate the value of the parameter. So when we estimate the value or location of a parameter, we're using methods of estimation such as those that we did last time, right? Decisions concerning the value of the parameters are obtained by hypothesis testing, right? The topic which we're going to study right now, right? So students often ask which method should be used on a particular problem, right? That is, should the parameter be estimated or should we test a hypothesis involving the parameter? The answer lies in the practical nature of the problem and the questions posed about it. Some people prefer to test theories concerning the parameters. Others prefer to express their inferences as estimates. Both estimates and hypothesis testing are found extensively in the literature of statistical applications. All right. So this is good stuff, right? The whole point behind this, the whole point of the whole class was to do this, to help us make decisions. All right. That was the whole point of everything. Now, when you guys get to your next statistics class at the 4-year school, right, you're going to learn how to make decisions for your individual majors, right?
This is algebra, probability,
Mm-mm. This is called inferential statistics.
this class, 23.5.
Oh yeah, probability and statistics with algebra. Yeah.
What is probability?
So probability is like the chance that something will happen. Statistics is when you analyze the data, you know. So now what we're doing now is we don't analyze it already. We got our numbers, right? But now we trying to make a decision about something. All right. That's what this is helping us to do. All right. Part of it. Part of it, right? So whenever you're doing a hypothesis testing question, right? The first thing you want to do is you want to state your hypothesis. This is step one right here. Matter of fact,
Oh, no.
yeah. Matter of fact, let me write that in. This is step one. Oh, shoot, it's not writing. Why you not writing? Oh, snap. I know you're not overwhelmed. Come on now, man. For real? It's like that? All right, take a minute. Take a minute to load. All right, take a minute to load. All right. So this is step one, right? So our first step is to establish a working hypothesis about the population parameter in question. This hypothesis is called the null hypothesis. It's denoted by the symbol HO, right? The value specified in the null hypothesis is often a historical value, a claim, or a production specification. For instance, if the average height of a professional male basketball player was 6.5 feet 10 years ago, we might use a null hypothesis that mu is equal to 6.5 feet for a study involving the average height of this year's professional male basketball players. If television networks claim that the average length of time devoted to commercials in a 60-minute program is 12 minutes, we should use the what's called the null hypothesis mu is equal to 12 minutes as our null hypothesis in a study regarding the average length of time devoted to commercials. Finally, if a repair shop claims that it should take an average of 25 minutes to install a new muffler on a passenger automobile, we would use the null hypothesis mu is equal to 25 minutes as the null hypothesis for the study of how well the repair shop is conforming to specified average times for a muffler installation. Right? It is good.
Like here,
Mm-hmm.
it's it's a, it's a
Me-
historical value,
Right.
talking about, a product, okay.
Yeah, or it could be a claim or a production specification. Right? So that's step one. All right. Whoops. Clicked on the wrong thing. 1 second. Yeah, go ahead. You got time. And I believe there's a homework question like this asking you to state the null hypothesis and everything. I'm gonna pull it down 1 second. Just give me 1 second. All right, there you go. All right. So any hypothesis that differs from the null hypothesis is called an alternative hypothesis. All right. An alternative hypothesis is constructed in such a way that it is the hypothesis to be accepted when the null hypothesis must be rejected. All right. You're fine. You're fine. You want cough drops? Okay.
Yeah.
Got you. It's kind of strong though. So you know. I can't seem to grab it.
There was a sign on the test that was weird.
What was?
It was like a O kind of, no, it looked
Oh,
like.
that's
A.
population standard deviation. It looks like an A.
Mhm.
Yeah. So then you know it's kind of strong.
It's okay.
So this is, the large testing the differences or testing statistics.
Sample statistics. Just the top one. That's it. But after the final, if you want to come back, I can teach you the other ones. All right. Yeah.
Burn,
That's it.
burn. Burn.
I got you. I got you. All right, so look, an alternative hypothesis is constructed in such a way that it is the hypothesis to be accepted when a null hypothesis must be rejected. The alternative hypothesis is denoted by the symbol H1, right? For instance, yeah, like H with like a lower subscript 1, right? For instance, if we believe the average height of a professional male basketball player is taller than it was 10 years ago, we would use an alternative hypothesis as H1 is equal to mu greater than 6.5 feet, with the null hypothesis of mu is equal to 6.5 feet, right? So null hypothesis, this is the statement that is under investigation or being tested. Usually, the null hypothesis represents a statement of no effect, no difference, or put another way, things haven't changed, right? But the alternative hypothesis, this is the statement you will adopt in a situation in which the evidence, the data is so strong that you reject the null hypothesis. A statistical test is designed to assess the strength of the evidence data against the null hypothesis. All right. This is good stuff. Let's start off with an example. All right. Now y'all got homework questions like this. Okay. Yeah. Hey. Mhm. So null and alternative hypothesis, right? Let's say a car manufacturer advertises that its new hybrid model gets 47 miles per gallon. Let mu be the mean of the mileage distribution for these cars. You assume that the manufacturer will not underrate the car, but you suspect that the mileage might be overrated, right? So, first question, right? What we going to use for the null hypothesis? What you think it is? Tell me. Yeah. For HO, what you think it is? All right.
What's that for H-O?
Yeah.
For H-O, it's, providing or product.
Mhm.
It's,
So what about the 47? It's Yeah, so it's the
Is the product specification?
mm, no.
No.
I'm looking for a Greek letter. It's
It's me, you.
right. So it's the mean is what? Is
You.
is 47. I'll take it. Right? So mu is equal to 47. That's it. Right? Mm-hmm.
So that's for you, right?
Yeah, well that's step one. Well, that's a piece of step one. That's a piece of step one. Yeah. Here go, yep. So here go the next question right here.
So, but you're saying is that you is 47.
Right.
But why can't it just be you and why can't it just be HO?
It's not HO. The hypothesis is that the population mean is equal to 47.
So then, no,
Mhm.
for you, oh, it's no.
No, we didn't even get that deep yet. That's coming. That's coming. Right. Here's a second question, right? What's the alternative hypothesis going to be? Yeah. So for H1, that's going to be what? So mu is, so what is that? Like in math terms? Huh? You know, but in math terms, is that it's like a less than
Then 47.
47. That's it. That's it. That's the whole step one. All right. There's a whole homework question on that. Mm-hmm.
Don't. Alright, fine. This is the homework.
Mm-hmm.
It's on the test that he gave us for tomorrow.
Oh, yeah, it's on that too.
It's not personal, going on page.
Unfortunately. Hmm. All right.
Wait, but why you put my, go up, my back, I'm gonna.
What happened? What happened? You want a picture of this? Am I?
But why did you put less than? Why did you put less than?
Because the mileage is overrated.
So overrated,
Yeah.
less than?
Like they, how can I say this now? You have this line of cars and they hype in the cars. Yeah, they exaggerate it so you think it's less. Yeah. Yeah. I'm not gonna lie though, there's some people, it's kind of shady, but there's some people who actually like look for things like this just to make a dollar. Like they would like say you make a claim about something, they run a hypothesis test and they're like, yo, your claim is false. They sue you over it. You know? Yeah. Some people make money off of that.
Like
Huh.
insurance.
Yeah, but like no, I'm saying like say you watch like a commercial or something and they're claiming something in the commercial, right? Like this medicine will cure cancer, straight up, right? And then someone takes it, you know, or they run like a statistic like this kind of test on it, right? And they see like, yo, I found someone that it didn't cure, and they sued them over it. Mhm. Mhm. Yeah.
That's why the commercial use of like what rate gives you weed, is
Yeah.
specifications now.
Yeah.
Really gave him wings? I swear to God,
Yeah.
that's
Yeah.
supposed to be out.
Same thing in Subway, the guy went in there and he measured the sandwich and he said it wasn't a foot long.
Mhm.
Are you putting your money,
My favorite was this medicine called Airborne. Yeah. Airborne used to be like, yo, you got a cold? I got you about that. Yo, that was the biggest hype, yo. Yeah, yeah. Overrated, like they're hyping it, you know?
Restaurant, right? And I'm telling you,
Yeah.
this restaurant is tough. It's the best restaurant in
Yeah.
town. And then when you
Yeah,
get
They,
there,
they got they got the best empanadas. Yeah, yeah. I'm trying to think of one. Now you know who I'm gonna throw under the bus? Golden Crust. Really? Depends on which one.
And which,
Yeah.
like, they uptown, White Plains, good. Down, mhm.
Well, 125th not bad.
Yeah.
Yeah. Yo, they got ice cream though. Yeah. Yeah. It's the Burger King of Jamaican food. Yeah, yeah.
One in Malcolm X.
That's good too.
Yeah.
Yeah. There's one over there. Yeah. Yeah, yeah, yeah. There's one by me over in Parkchester. They got that, you know? Yeah.
I just.
No, 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 no. That's real. That's what I'm saying. Talking about it. Yeah. It's another restaurant, a better restaurant. Yeah. Gold Spoon. Yeah, yeah. Yeah, that's like by
Yeah.
where is that by? Soundview. That's what I'm trying to say. St. Lawrence, yeah, around there. Yeah. Yeah, yeah, yeah. They're really good. Yeah. You know, I heard of that. Yeah. Yeah, 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 yeah. Tell you guys an interesting story, right? The CEO of Golden Crust graduated from BCC.
Yeah.
You know?
Yeah.
Yeah, legacy. Like you know what I think it was? I think he made too much money. And then he was like, yo, I can't no more. I'm earning too much. Oh.
What do you do when you have it all? Yeah. And you don't know what to do. And then, I don't know about
I know what to do with it, but how many people around me is genuine? Yeah. How many people around me is genuine? Yeah. Yeah. And I know him living in that community, everybody's like, no. And it's not like thank you, and it's more like all right, so let me make a little quick comment, right? So regarding the null hypothesis, in statistical testing, the null hypothesis, HO, always contains the equal symbol. However, in the null hypothesis, some statistical software packages and text also include the inequality symbol that is opposite that's shown in the alternative hypothesis. For instance, if the alternative hypothesis is mu is less than 3, right? So mu less than 3, right? Then the corresponding null hypothesis sometimes written as mu is greater than or equal to 3, right? So mu greater than or equal to 3. The mathematical construction of a statistical test uses the null hypothesis to assign a specific number rather than a range of numbers to the parameter mu in question. The null hypothesis establishes a single fixed value for mu so that we are working with a single distribution having a specific mean. In this case, the null hypothesis assigns mu is equal to 3. So when the alternative hypothesis, mu less than 3, is the alternative hypothesis, we follow the commonly used convention of writing the null hypothesis simply as the null hypothesis equal to mu is equal to 3. All right. Let's talk about types of tests. I got you. I got you. Well, we'll get there, right? Let's talk about the types of tests, right? This is step 2. Let me write that. Step two. All right. Types of tests. So the null hypothesis always states that the parameter of interest equals a specified value. The alternative hypothesis, H1, states that the parameter is less than, greater than, or simply not equal to the same value. We categorize a statistical test as left-tailed, right-tailed, or two-tailed according to the alternative hypothesis. All right. There's some good stuff right here. Yeah. We're talking about our tests now. Oh, shoot. Right.
Based on all this?
Mm-hmm. Well, this is just step two, right?
Oh, the one you gave us.
Yeah. So this is like right after we state the null and the alternative hypothesis, we got to figure out what kind of tests we're doing, right? So let's talk about the different types of tests. So a statistical test is left-tailed if the alternative hypothesis H1 states that the parameter is less than the value claimed in the null hypothesis. So mu is less than dot, 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 right? A statistical test is right tail if the alternative hypothesis states that the parameter is greater than the value claimed in the null hypothesis. So mu is greater than dot, 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 right? A statistical test is two-tailed if the alternative hypothesis states that the parameter is different or from or not equal to the value claimed in the null hypothesis. So mu does not equal dot, dot, dot. All right. That's our statistical test right there. It makes sense? No? Oh, crap. Oh, dang.
So wait,
All right, you know what? Let's try this again. Let's try it again. Huh?
that graph,
No.
that's one.
Oh.
Right. Tail, right tail, tail.
Yeah, yeah.
Tail.
Yeah. No, it's like Sonic the Hedgehog. Let's try it again. Let's try it again. Let's try it again. Huh?
I did it right here.
Mhm.
That makes sense.
Mhm. It's not done though. Yeah.
So.
All right. So let's try it again. Let's try it again. All right. You have the null and the alternative hypothesis for a test of the mean, right? Not yet. I'm just trying to explain the same thing again, right? So for your null hypothesis, right? That's your claim about the mean mu or the historical value of mu, whatever. So that's mu is equal to k, for example, right? Your alternative hypothesis has three types, right? So you have a left tail test, which means that mu is less than k, right? So you believe that the population mean is less than the value stated in the null hypothesis, right? You have a right tail test, right? Which means that mu is greater than k. You believe that the population mean mu is more than the value stated in the null hypothesis. Last but not least, you have a two-tail test, which is stating that mu does not equal k. So you believe that the population mean mu is different from the value stated in the null hypothesis. All right. So some other things that we could talk about, rho, that's our population correlation coefficient. Sigma is a population standard deviation. Mu1 minus mu2 is the difference of two means, right? And then you have P1 minus P2, that's the difference of two proportions, right? These are the other types of hypothesis testers that we can do, right? After the final, if y'all want, come back, I'll teach y'all how to do it. All right, it'd be real cool. All right. Huh? What? Probably. Probably. Just one more after this. At the 4-year school. At the 4-year school. Because it's gonna be, yeah, it's gonna be major Pacific at the 4-year school. You know? Every major.
No,
Yeah.
they said this is the only math I have to take, or associate's degree.
They lied.
Yeah.
So think about it like this, right? We're doing this class, right? I give you data. I keep giving you data, right? And then I ask you to analyze it. But how does that tie into your major? That's what the next class is about.
Yeah,
You know? So like, yeah, we all could get some data and calculate a mean. That's light, right? But how do you use that mean to make a decision, in your major, you know? This one. Yeah. Right. Like we just doing exactly. Exactly. Right. And applying the answer is as simple as writing a paper about it.
I don't want to.
I feel Huh? What happened? Yeah, we're gonna get to another example. I, I got you. I got you. All right, so in this introduction of statistical tests, we discuss tests involving a population of mean mu. However, you should keep an open mind and be aware that the methods outlined apply to testing other parameters as well, right? Such as rho, such as sigma, such as mu1 minus mu2 or p1 minus p2, right? So on and so forth. And again, in your next class, you guys will get into that. Yippee. Hmm? There's some good stuff here. Good stuff. I got you. I got you. Since you asked for it, that's what we about to do. Here we go. All right. I gotta explain it first. I gotta explain it first, though. So hypothesis test, I got you. We're coming. So hypothesis test of mu, given that x is normal and sigma is known, right? This is what's going to be on your test. So once we have selected the null and alternative hypothesis, how do you decide which hypothesis is likely to be valid? Data from the sample, data from a simple random sample and the sample test statistic together with the corresponding sampling distribution of the test statistic will help you decide. Our last example leads you through the decision process. First, a quick review of the last section, right? Recall that a population parameter is a numerical descriptive measure of the entire population, right? Examples of population parameters are mu for population mean, rho, or sigma, right? Our population standard deviation, right? It is important to remember that for a given population, the parameters are fixed values. They do not vary. The null hypothesis HO makes a statement about a population parameter. A statistic is a numerical descriptive measure of a sample. Examples of statistics would be like X bar or P hat or the sample standard deviation. Statistics usually vary from one sample to the next. The probability distribution of a statistic we are using is called a sampling distribution. All right.
You're fine. I think I work here.
I'm gonna give y'all all the tea right now. It's gonna be good. It's gonna be good. Got you. I got you. That's what's on your formula sheet, all right? So for hypothesis testing, we take simple random samples and compute a samples test statistic corresponding to the parameter in the null hypothesis. So based on a sampling distribution of a statistic, we can assess how compatible the sample test statistic is with the null hypothesis. In this section, we will use hypothesis test about the mean to introduce the concept and vocabulary of hypothesis testing. In particular, let's suppose that X has a normal distribution with a mean mu and a standard deviation sigma, right? Then theorem 7.1 tells us that the X bar, right, the sample mean, has a normal distribution with a population mean mu and a standard deviation of sigma divided by the square root of n. Here we go. This is what's on your formula sheet in chapter 9. right? Requirements, right? The X distribution has to be normal, right? With a known standard deviation sigma. Then X bar has a normal distribution. The sample test statistic, X bar, has a Z value with Z equal to X bar minus mu divided by sigma divided by the square root of N, where X bar is the mean of the simple random sample. Mu is the value stated in the null hypothesis, and N is the sample size. Right?
Oh, that means the vibe, right?
Right, yeah. It is the same formula that you saw in chapter 7. I'm not even gonna lie to you. It's the exact same formula. Yeah.
Yeah. Same as 4, right?
Yep, same exact thing. Because it all ties together. You know?
That is so true.
Yeah.
So in the test, right, in the final, is it gonna say like, this is from chapter?
Nope.
No, it's not gonna.
Use the questions. Use the questions. All right, so look at this. Look at this. Look at this. All right.
Yeah.
So look at this, right? This is how you could tell this is chapter 9 right here, right? It says Rosie is an aging sheepdog in Montana who gets regular checkups from her owner, the local veterinarian. Let X be a random variable that represents Rosie's resting heart rate in beats per minute, right? From past experience, right? The vet knows, glad Alex not here, this will be. From past experience, the vet knows that X has a normal distribution with sigmas equal to 12. The vet checks, right, the manual and found that for dogs of this breed, right, the average beat time is 115 beats per minute. So over the past 6 weeks, these are Rosie's heart rates when she went in, right? 93, 109, 110, 89, 112, 117, right? The sample mean, right? Sample mean means that I add up all those numbers and divide by how many numbers is there, right? Is 105. The vet is concerned that Rosie's heart rate may be slowing. Do the data indicate that this is the case? All right. So, what's my null hypothesis? Step 1.
So, right, about. Is this the formula X minus mu over?
No, not yet, not yet, not yet. That's coming. Yeah, this is just step 1. So what's my null hypothesis? What's my alternative hypothesis using a story?
When we put like 115.
So what is it for the null?
Yeah.
Okay, mu equals 115. Very good. So what's the alternative hypothesis?
Wait.
No, it's still mu and it's still 115, but what's the alternative hypothesis? Uh-huh. No. What's the inequality symbol I'm gonna put here? Is greater than, so her heart rate is increasing, right?
That's that.
Okay.
Wait, don't we have to put this in a row to see?
It's already done for us. There goes your mean. You know? Yeah. I know y'all know how to do that already. All right. So let me just write down a couple of things. We know that sigma is equal to 12. We know that our mean is equal to 115. We know that our n is equal to 1, 2, 3, 4, 5, 6. All right. Just write down a couple of things from the story. All right. Step 2. What kind of?
Don't hurt it then less. Because of the mean, because it keeps going up, right?
Let me see.
So because of 117, we know it's going up.
Oh, shit.
Maybe it says Rosie's heart rate may be slower down.
Okay. try to read this for myself.
I got you. Now, step 2.
Yeah,
Well, we're gonna make a decision on that. All right. So step 2. What kind of test is this? Is this a Z test or a T test? It's a Z test. Very good. All right. How you know it's a Z test? All right. But what makes you say it's a Z test? That's true, but what makes you say that it's a Z test?
because where X equals meaning, because of that example in the requirement.
Okay.
Cause the
Right.
letters matter, the letters that matter. They matter.
Which letter?
They-
So which letter though tells me to use Z?
Which next B equals has a normal distribution, the sample
Um, when do I use a Z distribution?
When you using, what's that formula? The name is
But when do I use it though?
What, a Z distribution?
Yeah.
Z distribution.
Low key, y'all could literally just copy from the formula sheet. Thank you.
what was it?
That isn't chapter 9. What?
Yeah.
No.
When sigma is known, that's the reason why.
Oh,
Right? Sigma is a good one. All right.
See, these are the keywords that I need for when I'm doing this. So that's what
Oh,
we got.
one is known, okay.
I forgot to write this.
Be known to you, for you,
Right?
yeah.
After that, you guys already know how to find Z, right? Just plug it in, blah, blah, blah. 105 minus 115 over the 12 over the square root of, y'all know how to do this already, right? Little, I got you. And then after that, just a little calculator. Yeah, everybody good with the calculator? You know how to type this in?
Wait, let me take it out.
I think it just be an app.
Right? That would help me so much.
I don't think twice.
They do, they got, I've seen them fancy
Yeah.
calculators and stuff.
Yeah,
You
yeah.
gotta do too much, like,
Mhm.
I need that.
That's the one. That's the one I've been using in class. All right, let's recap then real quick, because since you're here, I'm gonna do a special for you.
Here, show me how to, 105.
12 divided by what? Wait,
Because I had to just do it by hand. Like I subtracted the top. Then my answer, I just divided the denominator into my answer.
Nah, you don't gotta do it by hand.
we have to codify this?
Not really.
Did it like this.
Let me see. Yeah, that's fine. I'd rather you just do it all in the calculator. Yeah. Now, give me the decimal for it. Press the button right above. Mhm. Yeah. So look, specifically for you, right? This is how you type it in the calculator, right? This is your calculator. You go open parentheses, right? Then you type in 105 minus the 115. Then I want you to close parentheses, right? Then divide, right? Then open parentheses again, right? Now this is the 12. Then you're gonna divide. Then you're gonna do second square root. Then you're gonna do the 6. After that, you want to come out of the square root and then close parentheses. And so, second square root. Yeah, it should be negative. Yeah. Yeah, you could get it in the library or you could get it in CPH 303. Yeah. Ask for one it is. Yeah. Yeah.
Probably.
This is actually for her calculator, not for y'all.
Oh.
Yeah. She got like the original one. Wow, you got the good one.
No, you told me.
Oh, that's a good one. Oh, yeah, you gotta do the same thing.
That's
Yeah.
What? Yeah, hers is the one that I like.
Yeah.
That's the 500.
Yeah.
No, you don't have that. I think that's the same.
Y'all two gotta do it this way. It's this for y'all. Yeah. Right? Y'all gotta use them parentheses, all right?
But my division shot don't pop up like.
Yeah. That's all right. Even if it's like even if it's like dot, whatever, like that's fine. Same thing. It's the same.
the library cover.
It's like us, I worry about it. I like
Did you type negative or minus?
for some reason I like.
Oh, what happened to the division? When you do the division between them?
I did, that's cool, that's what I was saying. It's a different-
No, there's two divisions.
But the library calculator.
Oh, between the 12.
Yeah.
When I press. Yeah, that's what.
Uh-huh.
Which square button am I pressing?
The square root, the one that looks like this. Yeah, the house. Yeah, that's the one. That's the one.
Oh, you see, that's the.
Mhm.
Who I put.
This is right.
Square root first and then six.
Yeah, but here's where your issue is, right? You see how the parentheses is underneath the radical? So delete that and then come outside the radical, use the arrow key. Yeah. Let me see. Mhm.
Oh, gave me a fraction, don't piss me off. Let me see which one you got. You have this one?
No, not this one. Look.
Yeah.
Right?
When you converted it to a decimal.
So what you're doing is second and then this square root.
Never get that shit again.
And then six, and then close parentheses like that.
Oh.
Yeah. Mhm.
I heard.
I think so.
You think so?
Oh,
Alright.
Yeah. Format, fractions, to decimal, format, you hit format, and it's.
So I'm just gonna write down the answer real quick. Negative 2.041241. All right. Y'all get the idea?
Oh, you just press equal twice. That's good. Oh my God, okay, I got it. Thank you. Yeah, well, I really is from you.
All right. So we go with step one and step two?
Wait, yeah.
No, go ahead. I got you.
And that's right.
You need to start sending this Excel in those YouTube videos.
I got you.
Cause.
I got you.
Oh,
I got you. Oh Lord.
that's a shark. I'm even like hearing. Oh, yeah, where?
You told me all the lights and years.
Mhm.
What I'm supposed to do? This side of the house?
Bring them back to life.
Oh, God, no.
So I know some of y'all wondering about Rosie. Right? The dog.
Girl, that was just.
So this Rosie right here. What you mean that the whole problem was about Rosie? Yeah, that's Rosie. Okay.
Yeah.
Yeah. Nah. All right. So hold on.
If it was on the side.
True. Let's go one step further.
One step further.
Uh-huh. So this is kind of like a step three, but y'all could probably guess where I'm going with this, right? I gave y'all a Z value. So what do I want?
T guy.
No.
Deeper.
No, it starts with a P. I want the probability, right? So check this out. Check this out, right? I'm gonna show y'all something. So the probability, right? This is how you get something called your p-value, right? Look, good, good. So look, the p-value, right, is gonna be your z-test value that you just found, right? The inequality symbol that you're gonna use for the probability is gonna be less than, right? And here's how you know it's less than, right? Whatever your alternative hypothesis is, that's the same symbol you're going to use in your probability, right? So this is going to be less than, right? Why? Because it's what the alternative hypothesis is, right? After that, just plug in the numbers, look it up, same old from chapter 7, same old, same old. So this is what, negative 2.04, then we just going to go to the table, look it up, right? So let's
What? The
you tell me which table I'm looking at. But we're still using it. Yeah. So what was our probability again? What, negative 2.04. So which side am I going to? The positive or negative side? Negative side, all right.
negative.
No, no, hold on. It's not 2.04? Yeah, 2.04. Yeah, that's what we're looking at. All right. So we're gonna come to where negative 2.0 is. Then we're gonna look up top to where the 4 is, and we want to know where do they intersect that. What's that probability? 0.207. Very good. Right here, right? Negative 2 and the 4. They intersect at the negative 207. All right, let's go back. Mhm. So that's your answer. 0.0207. Right? That's step 3. We got more steps. All right. But y'all already know how to do this. This ain't nothing new. This chapter 7. Yeah. This ain't nothing new. Yeah, this ain't nothing new.
First of all, we learned in chapter 9 at once,
Yeah,
okay?
everybody does.
It's a 4-day process.
Everybody does. Everybody does.
In chapter 9, and I'm still stuck in chapter
Mhm.
2.
I'm
I got you. I got you. All right. Next thing I want to talk about is a little interpretation. All right. Because we already spoke about how to find the little p-value. All right.
Okay, so P value is in the chart. Wait, what's the?
The p-value, yeah, is in the chart. Yeah. Let me give you all a little bit about the interpretation, right? So, what conclusion can be drawn about Rosie's average heart rate? So, if the population mean mu is equal to 115 is in fact true, the probability of getting a sample mean of X bar less than or equal to 105 is only about 2% because the probability is small. So, we reject the null hypothesis of 115 and conclude that the alternative hypothesis of mu less than 115, right? Rosie's average heart rate seems to be slowing, right? So we have proved that the null hypothesis, which is mu equal to 115 to be false, and the alternative hypothesis, mu less than 115 to be true. No, the sample data do not prove that the null hypothesis is false and the alternative hypothesis to be true. We do say that the null hypothesis has been discredited by a small p-value of 0.0207. Therefore, we abandon the claim that the null hypothesis is equal to 115 and adopt the claim that the alternative hypothesis, mu, is less than 115. All right, so that's our interpretation of what we just did. Go ahead. What was your question? Yeah. Yeah, okay.
So in step, right, the P value is 0.02.
Oh, 7, yeah.
And what is this? What are you talking about here?
So,
Okay, for interpretation.
yeah,
So it's basically interpreting everything you just did.
right.
Yeah.
So basically, I wanted to know if Rosie's heart rate is actually slowing. This is the math behind it to prove that it is slowing. Mhm. Mhm.
I don't know, in my mind, it was just saying, this is the math to confuse you more, why it's slow.
Nah, to make your decision, and if it is or not. Because remember, y'all gonna be doctors one day, so y'all gonna have to make life decisions, right?
Yeah, it's my children. Everybody else be weird.
I mean, that's good enough. So look, the sampling distribution for an X bar distribution and corresponding Z distribution, right? So our population mean was 115, right? Hey, our sample mean was 105 right here, right? And then we found our p value, right? Which is less than our z value, which is negative 2.04, right? Just showing you how they correspond to it.
But it's the same, oh, it's different because of the size of it,
Right.
right?
One is an X bar distribution and the other one is a Z distribution. Yeah. It's it's just theory. It's just theory. To show you how an X distribution corresponds to a Z distribution, right? Yeah.
They kind of X.
But what I want you to pay attention to here is like this pink part, right? That's your p value. You see how small it is, right? That's why we're rejecting a null hypothesis, right? Because the p value is so little, you know? Had the p value been greater, then we would accept the null hypothesis that mu is true. Okay.
It's, all right,
That makes sense.
that line that's not touching, the pink line or whatever, what the higher it is away from the baseline, that means it's negative.
Mhm.
The bigger
It's
it
not,
is,
right?
the bigger it is, the more likely that it's true. The smaller it is, the less likely that it's true.
That was the top is pop.
They're the same. They're the same, the top and the bottom. It's just that the top is the X distribution and the bottom is a Z distribution,
But what's
just like in chapter 7. So X is the regular raw numbers. Mu is equal to 115, X bar is equal to 105, you know? But the Z, right, is when we change it into a normal distribution using the Z formula, X bar minus mu over sigma, yeah. Right? All that good stuff. Hey, how are you? You didn't get one yet? Take it. Did I give you your test two back?
Yeah.
You did? Okay.
So, cause, all right, we say, we're saying table of area to the left of Z, that's on A8 and A9,
That's what using the table.
that's there.
Yeah, that's using the table, right? That's more important for like chapter 7 and this, I guess, a little bit. Yeah. Yeah. So all the areas on that table that you're looking at are less than, never greater than. But what if I asked you a probability of Z greater than? What would you do? No, there's no greater than. No, no. If I said I wanted the probability of Z greater than 2.00, what would you do with that number that you found on the table?
You go to the.
No, you do the starts with a C. Confidence? No, no, no. The complement, you do 1 minus. Yeah, you do 1 minus that answer if it's greater than what I'm asking you. It's all right. Y'all got time to study it. So anyway, let's talk about the p-value, right? So the p-value of a statistical test. So Rosie, the sheepdog, has helped us to sniff out an important statistical concept, p-value. Assuming the null hypothesis is true, the probability that the test statistic will take on values as extreme as or more extreme than the observed test statistic computed from the sample data is called the p-value of a test. The smaller the p-value computed from the sample data, the stronger the evidence against the null hypothesis. Period. Hmm? Yeah.
Professor, I don't know how I was studying this.
We'll talk about it at the end, how to study for this. Hmm? Just because I'm on a roll. It's included in that. There's like one question on it.
That's the last question, right? Because I'm assume this is chapter.
I didn't look at it. It might be.
Yeah.
You got this order, right? Yeah, yeah. Just Thursday, just give it in. All right. So the p-value, sometimes called the probability of chance, can be thought of as the probability that the results of a statistical experiment are due only by chance. The lower the p-value, the greater the likelihood of obtaining the same or very similar results in a repetition of the statistical experiment. Thus, a low p-value is a good indication that the results are not due to random chance alone. The p-value associated with the observed test statistic takes on different values depending on the alternative hypothesis and the type of test. Let's look at the p-values and types of tests when the test involves the mean and standard normal distribution. Notice that in example 2 for part C, we computed the p-value for a left-tailed test, right? Because it was less than, right? And our next guide exercise, we'll do a two-tailed test, yippee. So p-values and types of tests, right? Let the Z for the X bar distribution represent the standardized sample test statistic for testing a mean mu using the standard normal distribution. That is, the Z for the X bar distribution is equal to X bar minus mu over the standard deviation over the square root of n. Same formula that's in chapter 9, right? This is a left tail test. For a left tail test, your null hypothesis is equal to K, mu is equal to K. Your alternative hypothesis is mu is less than K, right? P-value on the left-hand side, right? This is the probability of getting a test statistic as low as or lower than the Z for X bar distribution, all right? Let's talk about the other ones real quick.
I see where you put that.
All right, so right tail test, right? In a right tail test, your mu is equal to K, but your alternative hypothesis, H1, is mu less than, greater than K, excuse me, right? So our p-value is on the right-hand side, right? So this is the probability of getting a test statistic as high as or higher than the Z for an X bar distribution. Mhm.
No, like even around.
Like this?
No, down. Up, down. I don't know what the hell I'm talking about. No, I just want to see the bar.
The bars.
Yeah, just put them together.
Like these two?
The top and bottom.
Down, yeah, top and bottom.
Yeah, put them together so she can take a picture to them.
Let me see if I
That's what
can.
I'm trying to do.
I guess like that. Hmm? Hmm? We did one already. Same one we just did. Yeah. Well, we got more though coming. I got you.
So it's basically, if
It-
it's on the
it is like
opposite
that.
side, it's just greater than.
Right. That's it.
The complicated.
So let's complicate it a little bit more. Mhm. So this is not on your exam, but still want to talk about it just so you know. All right. So this is the two-tail test, right? The third thing that can happen, right? You have a p-value on each side now, right? But your p-value is cut in half because half of it is on the left, half of it is on the right, right? And then you have a z-value, right? Absolute value of a z-value over there, right? So the p-value is equal to 2 times the probability of z greater than whatever it is you're looking for, right? Remember that formula if you're going to do a two-tail, right? Not on your homework, not on the test, but just telling y'all about it. Whatever value you get for the probability, when you look it up, you divide it by 2. That's it.
Oh, so you didn't give us a problem?
No. I'm just talking. You know. Let's talk about types of errors. All right. So if we reject the null hypothesis when it is in fact true, we have made an error that is called a type 1 error. On the other hand, if we accept the null hypothesis when it is in fact false, we have made an error that is called a type 2 error. Right? So the next table indicates how these errors occur. For a test of hypothesis to be well constructed, they must be designed to minimize the possible errors of decisions, right? Usually, we do not know if an error has been made, and therefore we can talk only about the probability of making an error. So usually, for a given sample size, an attempt to reduce the probability of one type of error results in an increase in the probability of another type of error, right? In practical applications, one type of error may be more serious than another. In such a case, careful attention is given to the more serious error. If we increase the sample size, it is possible to reduce both types of errors, but increasing the sample size may not be possible. Okay? All right. Sum this up a little bit. So let's say you say that the null hypothesis is true, right? Then if you do not reject null hypothesis, the correct decision was made, there's no error. But type 1 is if the null hypothesis is true and we reject null hypothesis. It's a type 1 error, right? Now, let's say that our null hypothesis is false, right? It's not right. So, and we do not reject it, right? That's what's called a type 2 error. Well, let's say that our alternative hypothesis is false and we do reject it, then that's correct. There's no decision that needs to be made, no error. So good statistical practice requires that we announce in advance how much evidence against the null hypothesis will be required to reject the null hypothesis. The probability with which we are willing to risk a type 1 error is called the level of significance of the test. The level of significance is denoted by the Greek letter alpha, pronounced alpha. All right. Okay. The level of significance alpha is the probability of rejecting the null hypothesis when it is true. This is the probability of a type 1 error. The probability of making a type 2 error denoted by the Greek letter beta, right? And that's how beta looks, right? So we have methods of hypothesis testing require us to choose an alpha and beta value to be as small as possible. In elementary statistical applications, we usually use the alpha first, right? So we'll be giving this in your question. So the quantity 1 minus beta is called the power of a test and represents the probability of rejecting a null hypothesis when in fact when it is in fact false. All right. So for a given level of significance, how much power can we expect from a test? The actual value of the power is usually difficult and sometimes impossible to obtain, since it requires the alternative hypothesis distribution. However, we can make the following general comments. The power of a statistical test increases as the level of significance alpha increases. A test performed at the alpha equals 0.05 level has more power than one performed at alpha equal to 0.01. This means that the less stringent, right, we make our, hold on. So we make our significant level alpha, the more likely we will reject the null hypothesis when it is false. Using a larger value of alpha will increase the power, but it also will increase the probability of a type 1 error. Despite the fact most business executives, administrators, social scientists, and scientists use small alpha values, choice, excuse me, this choice reflects the conservative nature of administrators and scientists. We are usually more willing to make an error by failing to reject a claim, HO, right? Than to make an error by accepting another claim, H1, right? That is false. So next table summarizes the probabilities of errors associated with the statistical test. All right.
That's in table 3.
No,
Yeah.
we're still at 9.
0.05, and then for the negative or the funny.
Got you.
No,
I think it is, yeah.
it's not a funny.
I mean, the answer to every question is in the formula sheet.
So that funny A is alpha.
Alpha. Mhm. They say it looks like a fish, alpha.
No, it's right here. Right here.
Mm-hmm. Related.
We're gonna talk about how we apply that. So this is one.
So the probabilities associated with the statistical test, our decision, right? So the truth of the null hypothesis, that is true, right? And if we accept the null hypothesis as true, the correct decision, right, with corresponding probability is 1 minus alpha. If we reject the null hypothesis and say it's false, right, type 1 error with corresponding probability is called the level of significance of a test. If the null hypothesis is false, the type 2 error with corresponding probability beta, the correct decision with corresponding probability 1 minus beta is called the power of a test. All right. Last step. Concluding a statistical statement, right? What's this, like step 4? All right. So usually alpha is specified in advance before any samples are drawn so that the results will not influence the choice of the level of significance. To conclude a statistical test, we compare our alpha value with our p-value computed using sample data and the sample distribution procedure. How to conclude a test using the p-value and level of significance alpha. If the p-value is less than or equal to alpha, we reject the null hypothesis and say that the data are statistically significant at the level of alpha. If the p-value is greater than alpha, we do not reject the null hypothesis. All right. Everybody write that down. This is important. This is how you make your decision.
This is how you make your decision.
You compare your p-value to alpha.
Okay, so.
All right, everybody got that? Everybody got that? It makes sense?
Oh, H0.
It's HO. Yeah. Yeah. No, it is a zero. Like H0. Yeah, but they call it HO. Yeah. Yeah. All right.
So if it's less than equal to, then you reject
Right.
the first.
The null hypothesis. And if it's greater than, we do not reject. All right. All right. Now I know most of y'all gonna forget this on the day of the test. All right. Sometimes it's good to look at the original statistician that came up with it to make it make sense. So here you go. This who came up with it right here. Right. So if you're right. So if your p value, right, is less than your alpha, then the null hypothesis, you reject it. Right? All right. I feel you.
So mine is greatly reduced.
I feel you. We almost there though. We almost there.
Been done. What time does class end? I don't even know.
3:30.
5 o'clock tonight. All right. So in what sense are we using the word significant, right? So Webster's dictionary gives two interpretations of significance: having or signifying meaning, right? Or being important or monumentous. In statistical work, significance does not necessarily imply monumentous importance. For us, significant at the level alpha has a special meaning. It says that at the alpha level of risk, the evidence sample data against the null hypothesis HO is sufficient to discredit the null hypothesis HO. So we adopt the alternative hypothesis H1. In any case, we do not claim that we have proved or disproved the null hypothesis HO. We can say that the probability of a type 1 error rejecting a null hypothesis when it is in fact is true. Right? And that is alpha. All right, good stuff, good stuff, good stuff. All right, let me just get y'all with a summary. Got you, I got you. Just hit y'all off with a summary, and we're good to go. These are the 5 steps.
Every time.
Yeah. So like honestly, when y'all taking the final, that's my first time seeing it for this semester.
Out of how many?
There's a couple of them.
There's a couple.
Yeah. Yeah. All right, so basic components of a statistical test. A statistical test can be thought of as a package of 5 basic ingredients. So these are the 5 steps. All right. Step 1, state your null hypothesis and your alternative hypothesis and the present level of significance alpha. If the evidence sample data against the null hypothesis is strong enough, we reject the null hypothesis and adopt the alternative hypothesis. The level of significance alpha is the probability of rejecting the null hypothesis when it is in fact true. Step 2, this test statistic, right? What kind of test are we doing, right? On our final, what kind of test are we gonna be doing? A Z or a T test? Which one? Z test, all right? That's points on the final for free. All right. So test statistics and sample distribution, these are mathematical tools used to measure the compatibility of the sample data and the null hypothesis. Step 3, really important, find your p-value, right? This is the probability of obtaining a test statistic from the sampling distribution that is as extreme as or more extreme as specified by the null hypothesis than the sample test statistic computed from the data on the assumption of the null hypothesis is true. Step 4, test conclusion. All right. If your p-value is less than alpha, we reject the null hypothesis and say that the data are significant at the level of alpha. If the p-value is greater than alpha, we do not reject the null hypothesis, right? Just think for step 4, what would Snoop Dogg do? All right. Step 5, right? Interpretation of our test results, right? Give a simple explanation of your conclusions in the context of the application, right? So, right, let's say that I'm rejecting my null hypothesis, right? The conclusion would be, right, that there is enough statistical evidence to conclude that the null hypothesis is not true, right? Let's say I fail to reject my null hypothesis, right? I fail to reject my null hypothesis. Then the interpretation is going to be, right, that there is not enough statistical evidence to conclude that the null hypothesis is not true. All right. That's your summary right there. Yeah. Do we got time for an example or y'all feel good? All right. I mean, we already been through everything. All right.
And it's us to tomorrow, right?
Yeah,
What day is that final? What's on Thursday, right?
it's gonna be on a Thursday.
This
All right.
chapter
Well,
one.
today is Wednesday.
Today,
No, next Thursday.
next Thursday. Yeah, next Thursday. Yeah.
Paul giving back to us.
Yeah.
All right, we could call it at that here. So give me one second.